Alright, so today I'm gonna be explaining another important video with the title graphXForm, Graph Transformer for Computer-Aided Molecular Design with Application to Extraction. This paper in 2024. Generative deep learning has become pivotal in molecule design for drug discovery and material design. A widely used paradigm is to pre-train neural networks and string representations of molecules and fine-tune them using reinforcement learning and a specific objective. However, string-based models face challenges in ensuring chemical validity and enforcing structural constraints like the presence of specific substructures. We propose to instead combine graph-based molecular representations which can naturally ensure chemical validity with transformer architectures, which are highly expressive and capable of modeling long-range dependencies between atoms. Our approach iteratively modifies a molecular graph by adding atoms and bonds, which ensures chemical validity and facilitates the incorporation of structural constraints. We present graphXForm, a decoder-only graph transformer architecture which is pre-trained on existing compounds and then fine-tuned using a new training algorithm that combines elements of the deep cross-entropy method with self-improvement learning from language modeling, allowing stable fine-tuning of deep transformers with many layers. So we present the molecule by its hydrogen-suppressed graph representation, where nodes correspond to atoms and edges correspond to bonds. So if we have M, which is some molecules with atom A and bond B, then an action, so we want to perform some action xt on this molecule M. What is our action? An action in the action space is just one of the three types. You either don't change, which terminates the design of the molecule. You either add atom or either increment bond, increase the bond order, or you add atom. You add atom to a molecule. This action adds an atom of type J to the graph and bonds it to the else atom. Looks autoregressive because the next time step, we just, based on previous iterations, we try to capture another mask. What is the next atom? Do we have next atom so that we can use this add action? Or we should increment the bond, meaning that we are increasing the bond order between the two atoms, J and L. The bond order between two atoms, for example, hydrogen, carbon. We know the valence of carbon is 4, so up to 4 edges. Of course, it depends if all of them are hydrogen. But if we have, for example, a double bond here with oxygen, then already 4 valence is occupied, 1, 2, 3, 4. So this is a valid molecule. And so step by step, we add atom or increase the bond. For example, if here is just 1, we increase it, we increase the bond. So instead of hydrogen now becomes oxygen because we have increased the bond. So given a molecule and a sequence of actions, we will write for the challenge of this method is that it's very slow. And it's very noisy because when you add something, some added bonds, all everything may change because the global topology may change. So this is the risk of this approach. So let's carry on. Example of sequential application of actions. For example, here we added atom, then we increment the bond. The next action again increment the bond, but the next action we don't change anything. And we don't change, it means that we want to terminate the design of the molecule. So they did this. We aim to design molecules which maximize a predefined objective function. So the goal is to find pi, because our policy, everything depends on our policy. And the policy depends on the network parameter theta. So this theta, when we draw from the policy, different policies, then we have different, because the expectation is taken over finished molecule samples from pi. And then satisfying the constraint to ensure it is valid at every step. Of course, in satisfying validity, you should think about at training time and the test time. Test time is very easy. You just check it and just you don't allow the invalid molecules to be generated. But the training time, there are hundreds of methods for validity of molecule at training time. The thing that I like is masking, because which atoms are valid based on the bonds that are connected to other atoms. So you in training, when you want to train in Python geometric, when you say, for example, edge type, but you mask only those who have a valid bond order, depending on the configuration, because this is for all edges, the type for all edges, and you mask only that are valid. You can define different kinds of masks. So once it is masked, then you can type another kind of mask for a different purpose. Such as, for example, if you're in diffusion, if you're changing the alpha, the forward process, then when you are learning it, then you should change what are the nodes that stay with the same probability, what are the replacement nodes. And then that's it. That is the idea. So the policy networks takes a molecule as input and predicts probability distribution over next actions. And they used, as I said, molecule graph transformer, because this graph neural network, it has many benefits, but it takes k hops. It takes k layers to go from one node to another, which are k hop away. But the graph transformer doesn't care. Of course, the computational complexity of graph transformer is quadratic. So there is always pros and cons in using GNN versus graph transform. Here is very interesting. We use the batch-wise cross-entropy once we uniformly sample from the best found of molecules. Here we get the best found. And here we get the best objective. What is your best objective? What is these are the inputs as well. So policy is the input. Objective function is your input. Your initial molecule is input. The number of best molecules to keep is input. The minimum and maximum number of molecules to sample without replacement is also input. So we have this action distribution. So this is the flow of molecule through the policy network. So flow of a molecule through a policy network, we consider alphabets carbon, nitrogen, oxygen. Of course, in QM9 data set, we have fluoride and hydrogen as well. there are 5 atom types. So we have this graph representation. We give it to this transformer, and then we apply another layer to compute the logits of the probability, because we want to select the 11th atom as the second atom in increment bond. And these are the results and the objective. The first task focuses on the separation of we call it IBA from water, a common liquid extraction process. And so this is the experiment they did. So they compared with also reinvent transformer, junction 3 VAE. They compared with these very good baselines. And these are the top 3 molecules. This is a smile representation. It's very funny. When you open a parenthesis, it means you're opening a branch. If you do it again, it means that you're opening another branch in the same set. So it can be something like this. So any molecule can be represented with this smile, very interestingly. And if you work with RDKit library, you can convert any PyTorch molecule graph to this smile representation and vice versa. So it's very flexible. For example, here we have these structural constraints. Start from initial structure, maximum 7 atoms, here maximum 5 atoms.